First, you might want to stop at the UIUC database. That's the largest airfoil database that I'm aware of that's online. It's free. Just go on and you can search for any airfoil. So I've got the Clark Y airfoil here .dat. You can look at a GIF real quick and it'll just show you the shape. But then if we click on this .dat file, we can download that. So I'll download the Clark Y and save it. And then inside of let's see. Okay, now I've gone into the Xfoil. You also download Xfoil, and on Windows, I don't think you have to even install anything. You just open a zip file and it creates this folder here. And inside of the bin folder, so this is the Xfoil 6.96 folder, and then you go inside of bin and there's this xfoil.exe. That's the executable that we'll be running. So I've downloaded the clarky.dat file from the UIUC database, and you can see how it's organized here. It has some numbers at the top. This just tells it that it has 61 points that define the shape of that airfoil. And then this particular format is such that that it's organized from starting from the leading edge and then moving back along the top of the airfoil, and then it starts again at the leading edge and defines the lower portion of the airfoil in these XY coordinates. Well, the way that Xfoil needs the data is formatted a little bit different, and so you'll need to take this data, and I usually just use Excel to reformat the data so it looks like this. So this is a clarky.txt file now, and you see that it starts at the trailing edge and moves along the upper surface of the airfoil to the leading edge, and then along the lower surface of the airfoil from the leading edge back to the trailing edge. So it creates a complete loop starting at the trailing edge, moving along the upper surface, and then returning along the lower surface back to the trailing edge. So that's the format that Xfoil likes this data to be in. So I'm going to double click Xfoil to start that, and then I just type in load, and I called it clarky.txt. So it says that's a plain airfoil file, and we'll call it clarky. Now the first thing that I like to do when I load a new airfoil is check the paneling. So if you go to PPAR, that will allow us to look at how this airfoil is paneled currently. Now I like to set the paneling up to a pretty high number, so I'm going to change N to 240. So it will have 240 panels along the surface, and then you'll notice that Xfoil naturally likes to cluster these near the leading edge because there's pretty high gradients in geometry at the leading edge. However, we want to cluster these where there are gradients in pressure, large gradients in the flow field. And so I also like to change the trailing edge / leading edge panel density ratio to 1 so that it's doing the same refinement at the leading edge and the trailing edge. So I'll just type in T and 1, and now when I click enter again, now you can see that it's clustered those panels near the leading edge and also clustered them near the trailing edge. So these are the default settings that I generally use when I'm first working with an airfoil. So I'm going to hit enter again to go out of that, and I'm going to enter the Opper menu. In Opper, this is where we're going to actually run the analysis on this airfoil and get lift and drag and moment coefficients. So the first thing in the Opper menu is to choose if you're going to run that in a viscous sense or inviscid sense. Now for high Reynolds number things, you can get away sometimes with an inviscid solution, but for lower Reynolds number UAVs or low speed flight, you really need to run these with the viscous settings. So again, I'm going to show you another website that I use to calculate the Reynolds number, and this is aerospaceweb.org, and they have it set up really nicely here where you can choose first your unit system. So we're going to stick with metric today. You specify an altitude, and you can say whether that's in meters, or you can use, whatever measurement you want over here. And then we're going to say that we're flying at 20 meters per second and that we have a reference length of 1 meter. And once you input that information, you can scroll down to the bottom and it will tell you the Reynolds number that you're operating at. So we are at a Reynolds number of about 1.4 million for this flight condition. So when in Xfoil, when I change this to a viscous simulation by typing in VISC, it's going to ask for a Reynolds number. So I'm going to put in 1.4 e to the 6. That's 1.4 million. And the Mach number, we can also look at our Mach number. Let's see, this is a Mach number of 0.0588, which is really low. We don't expect Mach effects to be significant, so I'm actually just going to leave that 0 in Xfoil. You could put in that Mach number if you'd like in Xfoil, but it's not going to affect the solution very much. Okay, so now we're ready to start running simulations here in Xfoil. Before I start running these though, I want to do one other thing, and that's to change the setting called iter. Iter basically specifies how many iterations Xfoil is allowed to take in order to converge to a solution. The default is set at 10, which I think is really low, and so I usually set that up to 100 and allow it to iterate 100 times before it gives up on trying to find a solution at any angle of attack. Okay, so now we can just start running different angles of attack, and you do that by typing in alpha spelled with an F and then specify the angle of attack. So here's alpha 0. It took 26 iterations to solve this, and then in this separate window that pops up, you can see that it's got the information here: angle of attack, the lift coefficient, moment coefficient about the quarter chord, drag coefficient, lift to drag ratio, and then N crit, which is basically a measurement of how much turbulence is in the air. And I generally leave that at the default. That's based off of experimental data that they've found as a fairly good setting. But if you know what you're doing, you can play around with that number. But in general, I leave that as a default, and now I'm going to copy this lift, moment, and drag coefficient information into an Excel spreadsheet. So I've actually run this several times already over a series of angles of attack ranging from -6 up to 18, and I've copied out the lift, moment, and drag coefficient information. Now I should say before I switch over to this that you can automate Xfoil so that it runs a whole sweep of angles of attack and records the data to a text file. However, the drawback with that is that you don't get to see how each solution converges, or that information just flashes across the screen so fast that it's hard to really understand what's going on. So I prefer actually to run each of these angles of attack separately so that I can look at this convergence information here in this window. So for example, now I'll run alpha of -2 degrees, and I can see that that converged in 13 iterations, and then pull off the data, and I can just kind of see what the flow's looking like, and that's beyond the scope of what we're covering right now, but we could study these plots and learn some things about the flow as well. One other thing that I'd like to point out about running cases in Xfoil is that generally it's really helpful to kind of creep up on a solution. So I ran alpha equals 0, then I ran -2, and then I might run -4. You can see it had some challenges there, but eventually converged after 38 iterations. And then alpha -6, and that one actually took 80 iterations before it converged. So now before though, so I started at 0. I like to start at a really around 0, angle of attack of 0, and then move in the negative direction, and then move in the positive direction. But I don't want to jump from alpha equals -6 now to alpha equals +2, because that's a fairly large jump in angle of attack. That's 8 degrees angle of attack jump. So what I need to do is reinitialize. See, the reason that's a large jump in angle of attack is that Xfoil uses the previous solution as the initial guess to the new solution that you're looking for. And so if I were to jump to an alpha of positive 2 now, it would be starting from this flow solution of alpha equals minus 6 and working towards the alpha equals 2 solution. So I want to reinitialize the solution, and so you do that by typing init and then push enter. And now the next time I run any solution, this reinitializes the flow, so it's not working off of that previous solution. So now I would start back at alpha equals 0, run that solution, and then go up to alpha equals 2, and then work my way up into the positive angles of attack. So you don't want to take large jumps in angle of attack when you're working here with the viscous solver in Xfoil. You want to reinitialize probably at a low angle of attack, somewhere right around 0, and then work out, either positive or negative from that point. And the smaller steps you take, the more stable the solver is going to be. So maybe you want to do it by increments of 1 degree instead of 2 degrees, or sometimes I've even gone to a half a degree where I really need to refine some area.